This is video number 3 for the week. This is the full official plate tectonics lecture. I'll begin, of course, by sharing my screen. You want to remember that there are 2 versions of the plate tectonics lecture, okay? Like always, there's the full plate tectonics lecture found under the content tab. It's one tectonics. Or I've given you again a mini review PowerPoint, which is what I'm lecturing off of. And by mini, it's still 125 slides long. So you see how big and intensive this is. But I selected essentially the most important figures so that I could minimize the amount of time, of course, that you're stuck listening to me lecture, but also to highlight the key points. So you're responsible for looking at both material. Everything included within here is part of the larger PowerPoint, okay? So there's nothing not being covered. I just want to make sure that if you're a little confused as to why you see PowerPoints listed twice, once in its entirety under the content tab and once in a smaller version that I name mini, it's because I just sort of cut and paste the smaller sections here. First thing that hopefully you're going to notice is there's that figure again, right, that we left off of on our last PowerPoint. There's the dates. All right, so we're going to pick up exactly where we left off. But before we do that, sometimes I think it's interesting to give the ending first. Now, in a movie, of course, I would never want to do that, right? It kind of defeats the whole purpose of building up and watching. Same with reading a book. But in this case, I'm going to give you the ending first, because I feel that in this case, a picture or a bunch of pictures is worth 1,000 words. Okay. So I want you to think back to the dates we've spoken of. Okay, when we talked about Pangea, I'm going to take a pause here for a sec. I want you to put in your mind what date Pangea is. Hopefully you just said in your mind 210 to 100 million years ago. Again, starting around 300 million years ago, but focusing specifically and very specifically in a 30 million year range of 210 to 180 million. Now you'll notice that this first figure is dated before that, 540 million. And interestingly enough, it's the opposite of what we're used to seeing with Pangea. Remember, in Pangea, we're used to seeing an X through the center, right? So the equator is there as a horizontal line, but if we drew an X all the way down the middle, right here, we're used to seeing the land masses here in the center. Now that's not the case here. You'll see that all of the land masses are situated essentially all the way to the west, all the way to the east, and all along the southern hemisphere. But if we move on, look at the dates they move. Look at the land masses as it moves. There's that magic date of 300 million. Getting closer to Pangea, there it is. And there's our X, right? What happens from here, though, is also miraculous, right? So that's Pangea. Now we unzip. Now we begin the breaking apart of our continents. And voila, we get our present-day landmass. Let's take a look at it. Pretty interesting to watch it happen, right? So essentially, everything starts off at the bottom, goes to the sides, merges in the middle, smashes together again, now begins to break up again. If you think about something being equally weighted, let's say, for example, a boat, you've now completed lab 1, right? So why does a metal boat float? Because it's less dense than the water that it's in. Well, if we put all of the tiny little irregular shaped objects in the front of the boat would sink, right? If we put a bunch of cargo only on the front of a boat, the boat would sink because the mass wouldn't be distributed evenly. Same thing would happen here, right? If we had all of our land masses only at the bottom, only at the top, only on the sides, it'd be crooked, right? It'd be irregularly balanced. So what the Earth is trying to do is reach an equilibrium. It's trying to spread that weight out of water and land. And again, remember the water is just filling in the land over the land masses, trying to distribute the weight. Now, what's interesting though is if we drained the water on this map, literally took the blue off the map, the colored continents that you see are actually connected. Again, the bottom of a bathtub is a bottom, but if the bathtub water were black, you just wouldn't see the bottom of the bathtub. Here, the ocean is so deep and dark that you simply can't see the bottom in most cases. But you know it's there because when you go to the beach and you walk, even though your feet are under the water, they're standing on ground, right? It's sand. It's the eroded shoreline. You could technically walk all the way to the bottom of the ocean floor and pop up on the other side of the ocean. It's just that water is in the way. So what's really happening is then as the land masses are moving around, the water is just shifting location to fill in the spots. If you got in a bathtub, the water fills in around you. If you shift to the other side of the bathtub, the water moves around you. If somebody else gets in the bathtub, maybe now there's too much in the bathtub, the water might overflow. In this particular case, the water can go up and down on the coastal edges, increasing and decreasing based on if the water is melted or frozen and where we shift it to. So the visual that we see, I call this particular image what the Earth looks like as you fly overhead in an airplane. The visual of what you see is just where the water meets the land today in its present location. In the future, it might look a little different. The purple, this is the edge of present day, what they're calling the former position from 50 million years ago. In other words, North America is shifting to the west. We're getting further and further from our mid-ocean ridge in the system. It shows you where all the mid-ocean ridge systems are, and those are the locations where the plate tectonic boundaries are actually moving things apart. So you'll notice, for example, that you see these arrows going apart. In other words, it's splitting, the plates are shifting apart at the mid-ocean ridges. That's what's making all of that movement as we fly overhead in an airplane appear that the continents are shifting in the water. Really what's happening is the landmass is opening underneath. Think of the middle of your bathtub spreading open. That's what's happening underneath the water. Okay, so that's the general story of why these visuals look so different from way back in the day through Pangea to present day. So now let's do us a favor, okay? And we'll come back to the end of the story at the end of the lecture. But let's do ourselves a favor and go all the way back to the beginning and start the story. Remember, we had a whole bunch of dates. The first date that we were paying particular attention to was 13 billion, the Big Bang. You need to take an entire astronomy course to actually understand the cosmos, how the Big Bang operates, okay? And this class is not an astronomy class, so we're going to fast forward it and cover it about 2 minutes or less. Many of you know a lot more about this probably than I do if you're interested in solar systems and space. And if you are, you should definitely take an astronomy course here at Suffolk. But the general consensus of what the Big Bang is that again, 13 billion years ago, you had a lot of different stuff swirling about in the cosmos. Different weights, different densities, made up of different materials. Gases, matter, dust, things big, things small. In other words, think of just a giant collection of stuff, okay? That stuff, though, of course, needs to separate and form some sort of structure because it's spinning, right? There's a large swirl. And as things spin, you can see again the spinning here. As things swirl, they start to actually separate out and collect based on density and based on similarities. So materials that are similar are going to be made up of similar things. Maybe magnetized the same way. Maybe they have the same types of densities. Maybe they're principally connected to each other because they're made up of a certain type of material. And so likes collect together and dislikes don't. They essentially keep swirling and keep forming until they get to different distances, okay, through this hot, thick space. Okay, so this is the primordial Earth. Okay, again, one of the planets centered around the sun. So we've jumped ahead quite a bit, right? But what have we actually done? What we've shown ourselves is that we have a collection of similarities such that everything gathers around a center, sort of like a centrifuge, right? Everything gathers around a center star, and they're different distances from that center star, so they're different heats, okay? But also look, each of these, what we now know to be planets, each of these are different sizes. They're found in different locations, and if you were to go and look closely at any of those planets, made up of different things, right? Some have moons, multiple moons, some have rings, some are bigger and smaller, and not just because they're closer and further from the sun. It's literally a collection of similarities and dissimilarities, okay? So the Big Bang 13 billion years ago is essentially us saying that we had a collection of stuff that gathered in a circular path with similarities collecting together. The similarity, right? The collection of similarity that we're most interested in is our planet. Okay. What's special about us is that we're far enough from the sun, yet close enough from the sun that we can be heated, but aren't super hot, but can cool when we're further away from the sun, but don't freeze entirely. And so we supposedly are the only planet that has water and can support life. Now, we have found frozen water on different moons and on potentially other planets buried way down, some semblances, but there's no real hard and fast proof. But we do know, of course, that we have water on our planet. We have water in two forms, fresh water and salt water. And of course, we're going to focus specifically on the saltwater portion. But we can't have our ocean and our water with salt until we have our earth settled down. So we call this an unsteady earth, an unsteady state. Okay. You see a lot of heat, a lot of volatility. I think of this as a pinball machine, right? So if you had a bunch of different pinballs, not just one at a time, shooting from the cosmos, remember, while this is happening, the Big Bang and the collection of all of the planets equally settling into their own steady states are all occurring simultaneously. So there's still space dust, there's still asteroids and heat, a lot of electricity, and it's very unstable. Remember, there's no oxygen either at this time. So you're going to have a lot of heat and a lot of static and movement, which causes a lot of collisions. So that same pinball idea plays forward. Simultaneous with that happening in the cosmos, on the Earth's structure itself, it's beginning to harden and cool. So what you see here, magma, think volcano, right? Still happens present day. You could go to Volcano National Park in Hawaii and be able to see active volcanoes. Some cool, right? Some can be exploding at a certain time because they're active. Sometimes those active become inactive. But this steady state was essentially happening in various places on the planet where we were opening and having high heat areas, magma areas, and cooled areas. But you'll notice that what it does is it gives the Earth topography. It gives us a change in height. So you have lower areas, higher areas, even higher areas, even higher areas. Now imagine that this is our bathtub. If water were to fill in here, it would look like the ocean floor was flat, but we know that it wasn't, right? Because you can see what's underneath isn't. It's bumpy. And it wouldn't go over the entire planet. Certain parts would still be sticking up above sea level. So as we settle into our steady state, essentially what happens is after that volatility slows, okay, and we get the basic general formation of the rock types that make up Earth, you have a higher point and a lower point, and think of that as our bathtub. It begins to rain, and you essentially get Earth's structures that build and form over. So you have that rock structure in the center, and then water structure on the top. Why do you have that water structure on the top? Because of course the water has filled in the bathtub. Where'd that water come from? Rain. So once that volatility settles down, essentially all of that material collects in clouds, okay, and it's in the form of water vapor. And there's, of course, other gases there as well. Those clouds get really heavy, really dense. You learned about density in Lab 1. That density becomes so heavy that just like today, when the cloud gets too heavy and too filled with stuff, it pours. In this case, it poured down boiling hot water for literally millions of years, filling in the bathtubs. That hot water, like pouring hot water on rock, causes the erosion of rock. And also, when it pulls that rock apart and breaks it down into the sand that we know today, it also takes away the materials in the rock. So you get things like sodium and chloride. Those are the two chemical composition of salt. So in the weathering of the rocks, you actually have the creation of not only the bathtub, but the bathtub filled with salt water. So just a reminder now that we've covered 3 portions on this figure: 13 billion Big Bang, 4.6 billion the Earth formation, and 4.2 billion the ocean formation. We're now going to go back and take a more close-up look here of the Earth formation and what the structural Earth looks like. Here's the chemical composition and the concentric composition of our Earth. I call it a 3-layered concentric Earth. 3 layers, for obvious reasons. There are 3 layers. Concentric, circular, one on top of the other on top of the other. You'll hear me refer to this as the gobstopper, or I'll also call it the Tootsie Roll Pop. Now, of course, this Tootsie Roll Pop doesn't have a stick, but if you think about a Tootsie Roll Pop, it has a wrapper on the outside, the hard candy, and the Tootsie Roll on the inside. So it has 3 layers. The wrapper is not made up of the same thing as the candy, and the candy is not made up of the same thing as the Tootsie Roll. So, just like that, the Earth is not made up of the same 3 layers either. We have 3 layers named crust, mantle, and core. Don't worry about it being inner and outer core, it's just core. So this would be the wrapper, this would be the candy, and this would be the Tootsie Roll. Okay, one wrapped on top of the other on top of the other. And you'll notice not only do they have 3 different names and 3 different locations, but they're 3 different thicknesses. Look how thin the crust is. The mantle, thick. The core goes all the way through here, right? Thick. So 3 different locations, 3 different names, 3 different thicknesses. Shouldn't come as any big surprise, just like you have a wrapper, a candy, and Tootsie Roll, that they're made up of 3 different things, 3 different types of material. They have 3 different types of magnetism or movement, and their densities are different because, again, their size and shape or their mass and volume are also different. So our 3-layered concentric Earth is broken down into those 3 layers: crust, mantle, and core, found in that order from outermost layer to innermost layer. The outermost layer of the crust is the least dense, and the core, the innermost layer, is the most dense. So essentially, when the Earth formed, the core formed first. All the material that was similar, this is made up of iron, all of that iron that was hot and heavy compressed together. Then wrap around it the mantle. The mantle has plastic portions or liquid portions and hard portions as well, solid portions. That's where that magma was that you saw in that image of the primordial Earth, right? That's essentially where the material, the lava, comes up out of cracks in the core. And then, of course, the crust comes all the way around, and that crust is very thin, and that's the movable part of the plates. So in plate tectonics, we could be saying crust movement, but really it's plates. It's interwoven sections, interlocking plates like a puzzle piece that move around. The crust then moves on the mantle. Okay, so those are our 3 layers: crust, mantle, core. You need to know those in that order, from outermost layer to innermost layer, and from least dense to most dense. Now we've covered 3 layers so far, right? But we actually need to get very specific now and include 2 more, giving us a total of 5 layers. Okay, what are the other 2 layers? We're going to name the asthenosphere and the lithosphere as the official names of the completed concentric Earth. So the 3-layered concentric Earth in its basic form is actually made up of 5 layers. The crust is called the lithosphere. Okay, you can see the crust here on the top. There are 2 types of crust, oceanic crust and continental crust, made up of 2 types of density. They are sitting as part of the lithosphere, so that's the crust, and they sit literally on the moho, or the connection point of the mantle. That's the same thing as saying that if I put nail polish on my nail, the nail polish is sitting on my nail, but it can move. You take that nail polish off. The lithosphere, those are the plates, is made up of 2 types of crust, again, the plates, sitting on top of the nail, right? The nail on my finger, sitting on top of the mantle. The mantle then, and here's where it gets really important that you focus on this black box here. See how there's just this little bit of gray? That's this portion here. So the asthenosphere is the upper part of the mantle and the upper part only. The rest of the figure, the rest of this gray, okay, the rest of the material not included in this box is going to be the lower mantle. What comes next, of course, is the core in the center, which is not part of our story right now. So if we now were to label our Earth from the outermost layer to the innermost layer, from the least dense to the most dense, we would say crust, lithosphere, asthenosphere, mantle, sorry about that. You tried to use my finger and it didn't work. So let me start that over for you. Crust is 1, lithosphere is 2, asthenosphere is 3, mantle is 4, core is 5. Now we want to get specific into each individual component. So remember, the lithosphere was the outermost layer that included the crust. Getting specific with the crust, there are 2 types of crust: oceanic crust and continental crust. Now, it goes without being said that you're automatically going to say, okay, I'm going to find the continental crust wherever there's a continent, and I'm going to find the oceanic crust wherever there's an ocean. That is not the case. Originally, back in Pangaea, perhaps it was more common and more typical then, but really all it means, okay, for purposes of this lecture, all it means is continental crust is anywhere that the crust is made of granite, and oceanic crust is anywhere that the crust is made up of basalt. It's really important to realize that because you can find continental crust under the ocean. You can find oceanic crust above the water. Okay, so it doesn't tell us, even though the names seem to imply it, it doesn't tell us specifically where they're found. Next thing that you want to notice about those 2 types of crust is that their density is different. And this is what's really important for the story. If densities are different, and a higher density means it's in general heavier, then that should tell us that the oceanic crust is deeper down in our story, right? Deeper down in the Earth's concentric layers than continental crust. Now, this is what granite looks like, right? You can just look at your kitchen counter, but that's, what granite is. But if you look here, this is basalt, okay? This looks slightly different. This is pretty dark, and it's also more dense. So when you take a side view of the box that was the close-up on the concentric layer figure that we just looked at, what you're actually looking at, this is where the box would be, okay? What you're actually looking at is the 2 different types of crust found in 2 different locations sitting on the upper portion of the mantle. And now this is liquid, okay? Plastic is the word that your textbook is going to use. So that's mobile. So that's essentially making the crust float or move on top. Now, we don't know anything about any of that stuff because we're busy just spending our time at the beach, right? The beach is what's sitting on top of the continental crust as the eroded part away. It's just the eroded rock of what was found at the bottom of the ocean, eroding away underneath and washing up in the waves, and the continental crust that erodes away from its formation and again from upland erosion. Getting back to focusing specifically on the 2 different types of crust. Here we are, continental crust and oceanic crust. In this particular image, yes, the oceanic crust is under the water and the continental crust is above the water. But that doesn't always have to be the case. So again, don't focus on that. Instead, focus on the density. Oceanic crust is always more dense because it's made up of basalt. Continental crust is always less dense because it's made up of granite. Here's another close-up of that same section. Okay, here's our continental crust. This is our oceanic crust. Again, in this particular image, again, the oceanic crust is under the ocean and the continental crust is above land, but that's because I wanted to start off easy and sort of show you guys the beginning portions of how plate tectonic works. I also like this figure because it highlights all of the layers that we just discussed, right? So here's our crust, continental crust, and oceanic crust. They are part of the lithosphere sitting on top of the upper portion of the mantle. The mantle then extends, that's where the asthenosphere is, the mantle then extends all the way in, that's the non-plastic portion, and then you have a core in the center. Remember the core, you don't have to separate it into inner and outer core, just call the whole thing in the center, again the Tootsie Roll Pop, the core. Another cross section of the same image. Now this is starting to show you, hopefully coming full circle, the topography of how this whole thing works. Remember the image I showed you earlier of the bumpy earth, right? If we're to fill them with water, the bottom of the ocean floor is going to look bumpy and certain parts are going to be high and certain parts are going to be low. So now if we take that same concept and have our 3-layered concentric earth and we fill in the bathtub, what do we have? A bumpy bottom with high points and low points, all created because of the actual concentric, right here, the concentric circle. So this is the inside, this is a cross section, right? Here's the core, again, made up of iron in the dead center. Here's the mantle. There are plastic portions or liquid portions. Okay, these are represented to show you that it's moving. Harder, rigid portions. And then, here we go. The crust is sitting on top. So that lithosphere is sitting directly across. This is supposed to bring you even more full circle, again, bringing you back to that image that I just brought us to show you that there can be locations at the land-water interface or even far in the middle of land where the ocean floor is pushing up, forming new basalt, new oceanic crust, and that it isn't just under the water, near the water, right, that this stuff is happening. It's literally all about what type of rock it is and the density of where it's going to be found. This also reminds you that crust is made after the asthenosphere pushes it forward. So all of this used to be red and bleeding, so to speak, right? This used to be lava, but over time it hardened and it sat on top. So the crust is sitting on top of, again, what we call the liquid or the plastic portion of the asthenosphere. So that's the background. Just taking a drink. Okay, so that's the background concept of what's happening sort of behind the scenes. How does anybody know that any of that is the case? We have to go back to the theory of the two concepts of continental drift and plate tectonics to be able to realize, one, how this stuff was discovered, and two, to put proofs behind the fact that they actually are the current scientifically accepted methodology for the actual concentric layers and structure of the Earth that we now call today plate tectonics. Okay, so we study this because one scientist can understand the principles behind Earth's formation and function, which of course started at the Big Bang, went through Earth's concentric layers and then the ocean formation. We can then understand how continents were formed, how they shifted, and of course we know they shifted because all those maps I just showed you show that they were not the same 540 million years ago as they are now, and of course why the oceans are located in specific regions. It also explains that we have present-day tectonic activity. A tectonic activity, by the way, is a rupturing volcano, an earthquake, a rift, a fault line. And you know we have all those present day. So it explains what's occurring present day, and it also explains why our maps look different then than they do now. So starting first with continental drift, because it comes first, our first proof or concept that allowed us to actually question why were the continents moving was that actual map that you saw of Pangaea. Remember, starting about 300 million years ago, getting more specific, 210 million years ago, the final split was 180 million years ago. The continents are still drifting today, which is again why I showed you a figure for 50 million years into the future. So this is still an ongoing story. So if all we have is a couple of maps and the maps look different then than they do now, and we believe that at one time all of the continents were touching in one big super landmass or one big supercontinent, how are we going to prove that that actually was the case? Well, what we can do is we can go and look at the edges and we say, did they ever look like they could have fit together? And sure enough, absolutely they can. Okay, so we have South America and Africa, present day, right? Again, you can see North America pretty easy right here. But they look like they fit pretty good. So if that's the case, and they were technically pretty close to being side by side not too long ago in the giant geologic time frame of this, then we should be able to go and actually sample the rock here and sample the rock here and find similarities, right? Because if they used to be the same and they were connected, then certainly there should be some stuff that's the same. Similarly, like putting a puzzle piece together, if you can move them around and fit them in so that they fit pretty well like a puzzle, then maybe perhaps they actually did fit together. Now you're going to see there are some overlaps and some gaps, which naysayers in the beginning thought proved that this didn't fit. But remember, if you took a plate, an actual plate, dinner plate, and you smashed it, would it smash in straight lines? Absolutely not, right? And then when it smashed, you'd get big parts, but then you'd get all those tiny, tiny, tiny little parts that you're sweeping up for like a week, worried that you're going to step on them, right? That you still find a week later in the vacuum. All those little teeny tiny parts, those vulnerable parts, when these things break apart, that's what's this, right? This explains that those edges are never able to go perfectly back together because they weren't perfect in the first place. So those edges, those overlaps can be explained. But by and large, there better be some major similarities where we believe those edges matched. Here's a figure that you saw in the last PowerPoint that again gets us to the same concept of what Pangaea looks like. It explains that there should have been not only a connection of land masses, meaning the types of rock should be the same, which we can radiocarbon date and prove are the same type and age, but there should be actual living structures and ancient fossilized material such as coal beds that you can find along structural lines, and they should be able to be again identified and radiocarbon dated as the same. So if the picture, of course, that we just saw was of Pangaea, and our present day picture looks like this, then we should be able to put all these puzzle pieces back together. And sure enough, we can. Okay. I want to pause here for a second and point out that in Lab 2, when I give you the instructions for completing Lab 2, I said that there's a figure at the top of the page that can be found in color in the PowerPoint that's easier for you to work off of for the lab. This is that figure. Okay, so this is the figure that you should be working off of with Lab 2 if you want to use it in color. In this PowerPoint, of course, the reason why this is here is because it shows us the edges and the boundary lines of our present day map, not of the original Pangaea map. So when you take all of those edges, you'll see that they're not perfect lines. You will also see that you have multiple plates. So if you break a plate, it doesn't smash necessarily into two pieces. Our plate, right, our crusts have now broken into between 15 and 17 plates, depending on which scientist and which textbook you read. Some are major and some are minor. So this is our present plate tectonic map. Alfred Wagner, 1912, is who we call the scientist that discovered and coined the term continental drift. The term continental drift is literally a play on the name. Continental, meaning continental crust, moving or drifting. Now, he didn't know at the time the difference between continental crust and oceanic crust. We now know that continental crust is less dense, so it's easier for it to move in the water, right? And it's essentially like a rubber ducky moving, but with the feet still touching the bottom. So as the Earth's crusts at the plate boundaries open up, the lighter portions can move. Now, flying overhead in an airplane, we called the things that we thought were visibly moving continents. So we would say, wow, it looks like the continents are drifting in the bathtub. The continents are moving freely in the ocean. They weren't, of course, right? They were attached at the feet. You just can't see it because it's so deep. So he coined the term continental drift to be a visible description of what was occurring. He then set out to try to find some evidence for his theory. The first bit of evidence, of course, was the fit of South America and Africa that I just pointed out to you. So I say, for example, puzzle pieces were fitting, and that fossil evidence was actually found. So I had pointed out coal evidence before. I talked about radiocarbon dating before. He also found coral, rock type, and reptile fossils to be found on two different continents, present day, right, in 1912, but that showed that at some point in ancient history, the edge of South America and the edge of Africa had to have been connected. And so they were. And now we found hundreds of thousands of examples of things like this to prove, by and large, that not only do we have puzzle pieces as evidence, but we have fossil evidence as well. Is another image, again, pointing out that we don't just have reptilian examples, we also have plant examples, and again, coral, coal, and dating. We start first in 1912 with that continental drift idea. About 50 years later, a scientist named Wilson comes in, and he changes the term from continental drift to plate tectonics. So we now know that continents, okay, are just simply what we call the land masses that stick up above the water. But really, we have two different kinds of plates. Plates that are made up of oceanic crust and continental crust. The plates then break apart via a tectonic event, an earthquake, for example, and it pushes the plates apart or together or slides them side by side like a sliding glass door. Those plate tectonic events then make what is sticking up above the water look like it's moving. So plate tectonics 50 years later was able to come in and now give the actual explanation behind why it looked like the continents were drifting. So continental drift is a visible description of what Wagner saw. Plate tectonics is scientific proof, the evidence behind why the continental drift was occurring. We now know that the plates are moving about 5 centimeters a year. Some move faster, some move slower, right? That's about an average. Some move more rapidly during a time of a tectonic event. Some could take time before there's any movement. And the plates themselves are powered by, first, the downward pull of the descending plate's leading edge. So let's dissect that for a second. Downward pull. So imagine that if you stood up and you had your two arms hanging down and your little brother or sister pulled on one of your arms. The arm that got pulled on would be the side of your body that got pulled downward, right? The other arm would not equally go down. So whatever side of the plate was being tugged on would be the one that moves inward into the earth, right? Into the mantle. It would descend, like going downstairs, it would descend into the mantle. So that arm of yours that gets pulled down, that would be the plate that would get pulled down into the mantle. As it gets pulled down, remember the mantle is boiling hot. So it essentially gets recycled up. It gets burned away. Simultaneously with that happening, the friction that's occurring in the asthenosphere creates the convection current, okay? And the convection current itself is what allows the asthenosphere to be plastic. So if you've ever seen a convection oven, it allows for things to be evenly cooked, evenly heated. Remember, the asthenosphere is the upper part of the mantle. It's the upper portion that allows essentially for the circular path of the heat source to cause that lava, to call that magma, to allow that red portion to be able to push up and push those plates out of the way. So bullet point number 1 is telling us that the descending plate is moving into bullet point number 2, the asthenosphere, because the convection current underneath it is causing the boiling. Okay. Another thought process, another way of approaching this is if you put a pot of water on your stove and you heat it up. The heat source is on the stove. So the bottom of the pot is going to heat up before the top of the pot. But eventually, once that whole pot of water is equally heated, you get a rolling boil. But the bottom heats up first. So obviously the asthenosphere is heating up, causing the convection current of the heat source to eventually get through the whole pot, to eventually get through the whole mantle. And when it gets to the top of the mantle, you're then in the asthenosphere, which is underneath the lithosphere, which is where the plates are. So that rolling boil then allows for the plates to be heated on the top, which pushes one inward, allowing it to be recycled. And finally, simultaneous with that happening on another part of the ocean floor, the sea floor is pushing open, again, because of the asthenosphere's convection currents. It's pushing open, creating new sea floor. So it's a 1-2 punch. Ocean floor is being created in one spot and recycled or lost in another. So the earth never gets bigger, it never gets smaller. It literally just changes shape, which then pushes the plates in different directions and makes it look different as you fly overhead in an airplane. So as I had said, Wilson was the scientist principally responsible for plate tectonics, and the Earth is now presently divided into between 15 and 17 lithospheric plates, which then contain our 7 continents. They meet at the plate boundaries, again, where the plates will meet, and they will do one of 3 things: diverge, which means move apart, converge, which means come together, or fault, which is to slip past each other. We call that a transform plate boundary. So the 3 plate boundary types are divergence, convergence, and transform plate boundaries. Bottom, Pangea; top, present day. We want to explain through plate tectonics how we got from B to A. And back again, right? Even from 540 million years ago to 200 million, how'd we get there? From 200 to present, how'd we get there? And where are we going now? Because remember, this is an ongoing story. So essentially what's happening is you're opening up parts of the plates, pushing things apart, which is causing things to collide on the opposite side. This is a picture of the Wilson cycle. So Wilson, again, is that scientist who coined the concept or the theory, which is now widely accepted, of plate tectonics. The Wilson cycle represents the 2 portions of plate tectonics: divergence and convergence. Okay, so 1 through 3, divergence; 4 through 6, convergence. Do not worry about memorizing all of these stages. You do not need to memorize them, okay? That's getting in too much detail. What I want you to pay attention to is in the top 3 stages, you have an opening, okay? Here's the asthenosphere. There's our convection current. There's a circular path here causing the heat source. It pushes up, it causes a break. It cracks down the center. That's our mid-ocean ridge. It's then going to cause this side of the plate to move to the right and that side of the plate to move to the left, just like these arrows are showing. As that shifts apart, it's going to lower the edges of the land masses, opening up more space for the seafloor. This is just later in time. Larger ocean, less landmass with lower on either side. So that's divergence, to diverge. Second half of the story is down below. If things are opening up on one side, the Earth can't get bigger, So it has to crash together on the opposite side. So notice how the arrows have shifted inward. Now our ocean system, our water body is going to get smaller. Our land masses are getting higher in height, even closer together, even less water, higher in height, and finally the highest in height of all, and no water at all. So you go from water filling in the bathtub to water being pushed from the highest mountains. And where would you find the water in this picture? On either side of what we call a continent, but really it's on either side of a plate. And that's how the Wilson cycle works. Divergence 1 through 3 and convergence through 6. There are some crazy examples in the middle of apparently nowhere. This is an example in Australia of literally ocean floor sitting high above sea level. There's another example in Iceland where the mid-ocean ridge system actually goes above sea level as well. So these are other proofs of what appears to be sort of a mistake in the creation of our geologic landmass, but really it just proves how plate tectonics has worked over time. There are a series of labs that you're going to be completing to get through this material, 4 labs to be specific. Lab 1 focuses specifically on density. The reason why you're covering all this material in lab is to go through the actual principal concepts of plate tectonics and the proofs that plate tectonics occurred. Remember, there were 2 proofs that continental drift occurred. Think about what they were. Hopefully you just came up with puzzle pieces, right? That the edges match in the puzzle, and fossil evidence. In plate tectonics with Wilson, there are going to be 6 proofs. Proof 1 is going to be density, and that's going to be what you study in lab 1. Remember, density is mass and volume. So how does density apply to plate tectonics? Well, we know that we have continental crust and oceanic crust, and they have different densities. The oceanic crust is more dense, so it's deeper down in the concepts of how our plates are moving. It's also heavier, so harder to move. So we're going to have a density differential, okay? Second proof is going to be the age of the seafloor as it plays out with proof of paleomagnetism. We haven't talked about the core yet too much, right? So the core is going to come into play with paleomagnetism. So let's go through 2 of these quickly. Just a quick reminder, of course, what density is. You measured it in lab as grams per milliliter or grams per cubic centimeter, but it's defined as mass per unit volume. So if you have granite, it has a different mass per volume versus if you have basalt. So what you're essentially doing is saying that the Earth not only is concentrically layered, but it's density stratified. With the least dense on the outside, that's our crust, more dense in the mantle, and the most dense in the iron center. You guys had to work through why a metal boat floats. I had given you an example that if you put all your cargo on one end, you're going to tip your ship. You have to equally load the cargo. So of course, what the Earth ultimately needs to do is equally move the plates around so that not too much is sticking up above the water, not too much is being pushed into the asthenosphere, that you have sort of an equal balance of granite and basalt with highs and lows, because it ultimately wants to have isostatic equilibrium or equal weighting. You guys know that to be buoyancy, right? The lithospheric plates are going to float in the sphere, okay? And instead we're using a boat and cargo, and it puts a different amount of pressure in the asthenosphere, or in this case, in the water. Here's what the example looks like when you apply it to plate tectonics. So there's our continental crust on the top. It has a weight, it has a density. It's heavy. It's sitting on top of a mobile convection current in the mantle. It's getting pushed up or down depending on what's happening on either side of the plate, which ultimately causes the center to cave in, reaching isostatic equilibrium or isostatic readjustment with erosion at the edges. So that's the first proof. The second proof is paleomagnetism. Let's break the term apart. Paleo, fossil or old, magnet. Okay, so the remnants of magnetic field of a rock fossilized. It means we can actually go back in time and use a magnet, just like those cool things you buy at Spencer's Gifts, where you have the shavings, or even an Etch-a-Sketch, where you have the shavings and then magnets can pull it toward or away from the center. That magnetic field will actually cause us to realign over time. So the core is in the center of our three-layered concentric Earth, and what it actually allows us to go back and do is not only find fossil evidence on the land masses themselves of reptiles, for example, but fossil evidence of the magnetic polarity, the push and the pull, the plus and the minus charges in our rock layers. So this is present day, and this is going back in time, okay? We're looking along the mid-ocean ridge, so the center of where a plate boundary would meet, and you're able to see that it has an equal amount of space, rock type, and density on either side of the break. Okay, so this would be an example of divergence. Okay, we're pulling apart at the break. So this is the zipper. This is where it's going to unfold. So if you were to pull that zipper apart, and these are pulling apart more and more over time, on either side, you should find the same material and the same density, and that's represented by the blue and the blue. Going further apart, orange and orange, yellow and yellow. There'd be pink and pink. What that's showing us is not only do you have the same rock types, again represented by the colors that match, but the polarities change as well. So here is your reverse polarity on either side of the mid-ocean ridge. Then you have a normal polarity. These two red move away as new ocean floor is formed. This all then moves away, that's this image, as these new ocean floor areas are formed. So again, 1 through 3 of the Wilson cycle, you see how this is opening up over time, okay? It goes from a skinny ocean with not a lot of room for the bathtub to be filled to a wide ocean with more room for the bathtub to be filled. If you went and you looked at the bottom of the ocean floor, you're seeing that what's actually happening is not only are the crusts moving, you're creating new crust in the center, and every roughly 3 million years, right? 0, 3, 6, 9, 12, 15, and onward, roughly every 3 million years, the polarity will shift, which is causing the change of the movement of which way, the direction, which way the actual plates are going to open up. That is paleomagnetism. Here's another cross section of the same concept. Another cross section, same concept. Paleomagnetism is going to be covered in lab 2. You're actually going to be cutting out, I believe it's page 18 or 19. It's a page in your lab book that has 2 long lines, and it asks you to cut it out with some scissors, to color it, to place it through a center, and then pull the actual 2 sides simultaneously to the right and to the left. And it's going to show you what paleomagnetism looks like as it pertains to plate tectonics. Here we are. Here's North America. The mid-ocean ridge system is about 1,500 miles off the coast. It's on an angle about 11 degrees to the east. There's an island called Iceland that sticks up above the water in seemingly the middle of nowhere. Here's Greenland, okay? Iceland, if you were to go there, literally has a mid-ocean ridge system above the sea surface. That's because as everything is opening and closing along that central line, stuff gets pushed higher and lower based on location, density, and polarity, so that sometimes you can have things above sea level, ocean crust, that you think should be at the bottom of the sea floor, and that's because they used to be. They just now have been pushed high enough up. Over time, though, of course, there's potential that this could be equally crashing in from isostatic equilibrium and found below. So now we gave 2 proofs of plate tectonics. We're going to go through the remaining 4 proofs, which give us number 3, 4, 5, and 6. So remember, 1 is density, 2 is paleomagnetism, magnetism, which again we just covered and that we did in 2 labs. And then the remaining 3, 4, 5, and 6 are going to be covered in this next part of the lecture, starting first with age of the seafloor. So what's interesting is if you were to go and age the Earth, continental crust is going to have a certain age, and oceanic crust is going to have a certain age. But oceanic crust can be made new. It's made wherever the divergent plate boundaries are found, and new basalt forms as it hardens, where the asthenosphere comes through those cracks. So the maximum age of the seafloor is Pangaea. Continents, on the other hand, are roughly the age of itself, right? 4.6 billion is the Earth, 4.2 is the ocean. That's roughly in the same ballpark. Because when the concentric layers were formed and continental crust was made, remember, made up of granite, that was formed because the gobstopper, right, this 3-layered concentric Earth, was forming with that on the outside. The inside, though, can produce basalt. Basalt can then form new and become what we call the seafloor. So if the seafloor can be created and continental crust cannot, then the seafloor must be the youngest portion of the crust. So if that makes sense, and we know where our mid-ocean ridge systems are, the middle of the ridge systems, known in the middle here with the red line, well, sure enough, then we should be able not only to identify where these ridge systems are, but we can actually age them. We can say how old they are. And look at this. Any mid-ocean ridge system is young, between 0 and 2 million years old, because again, that's where new basalt is forming at the center of the mid-ocean ridge system. And as you move away from the mid-ocean ridge system, the ocean gets older, with the oldest being in Pangaea's time. So the ocean is oldest at the edges, youngest in the center. Why? Because that's birth. That's the new portion and the new creation of basalt. I want you to take a look at this figure though and make sure that you understand that a mid-ocean ridge system does not mean the middle of a continent. It doesn't even mean the middle of an ocean. It literally means the middle of a ridge. Okay, so for example, here's the west coast of the United States. This is the Pacific Ocean. The middle of the Pacific Ocean would be like that. The mid-ocean ridge system in the Pacific is over here. Okay, so mid-ocean ridge does not mean mid-ocean. It means the middle of where the ridge systems, where the plates are meeting. In this particular example though, what this figure is showing you is that the mid-ocean ridge system shows us for a fact that the middle of the mid-ocean ridge is the youngest in age. So the ocean is youngest in the middle of the mid-ocean ridge, and it gets oldest at edges. Because what's happening at the edge? What's happening here? That's continental crust. And continental crust is even older than oceanic crust. So here we get to 200 million years old. This is on order of billions of years old. The next proof is the pattern of earthquakes and volcanoes. They were found by Wadi Benihoff. So sometimes you'll hear earthquake boundaries, also called subduction zones, also called Wadi Benihoff lines. And we believe that this relates to the idea of continental drift because it was the explanation of why it looked like things were shifting. So the area where this is most prominent is in the Pacific Ring of Fire. And it shows that if you look again at the mid-ocean ridge system, plotted in between Wagner and Wilson's time, if you look at that mid-ocean ridge system, and then you plot earthquakes, all these red dots are earthquakes, the earthquake boundary better match up with the mid-ocean ridge boundary. Here is the mid-ocean ridge for the Atlantic. Remember the one I just drew for the Pacific? There it is. So sure enough, the mid-ocean ridge system matches up perfectly with the deepest of the ridge systems, and the deepest focused earthquakes being at the deepest portions of the ocean. So where the Mariana Trench is, the Challenger Deep, the Japan Trench, all of that portion of the world, that's what we call the Pacific Ring of Fire. It's where the deepest components are found. The next example is called a hotspot, and you're going to have some questions about this in lab 4. Hotspots are surface expressions of plumes of magma rising from stationary heat sources in the mantle. Now that description sounds really scary and hard to understand, but then you see an image and hopefully it helps you make sense of it all. So remember we talked about isostatic equilibrium, right? Isostatic is us trying to have neutral, right? A balance. Isostatic sinking, though, is telling us that a plate, remember a lithosphere is 2 types of crusts, that a plate is sinking into, this is representing the mantle, okay? This is representing the actual convection current in the mantle. Now think of the eruption that's happening here. If this were to erupt through, it pops up and pushes land above water and then gives us a volcano, right? Or an eruption. That volcano hardens and becomes an island. Okay, in this case, one of the Hawaiian Islands. Now, this surface plume doesn't move. Imagine that's the heat source on your stove. This is the key part to understanding this. But look where the plate is going. This entire plate is shifting over the plume. So if you were to put a heat source on your stove and put the pot immediately on top of the heat source, sure, you'd pop out of the top. But what if you take that pot and you slide it past the heat source? Now the other side of the pot gets heated and a new pop or a new plate, right? Plate expression or plume pops up. So you get multiple islands along the way. The heat source stays stationary. This never moves. The plate is moving along that source. So it shows you the entire chain of Hawaiian Islands, all formed from one stationary, doesn't move, heat source. And that is the end of the proofs to plate tectonics. Present day Hawaii, again, showing you the proof of what those stationary plumes look like and what Volcano National Park looks like. Back and take a look at those 6 proofs one more time, just so we can go over them again. Remember, proof 1, density. Proof 2, paleomagnetism. 3, age of the seafloor. Younger in the middle, older at the edges of oceans, oldest even more on continental crust. Proof 4, earthquake lines. That means that the earthquakes, the tectonic events, match up with the plate boundaries. Proof 5, Wadi-Benioff zones. Those are the areas essentially where your deep focused earthquakes match up with your subduction zones, or again, plate tectonic boundaries. And hotspots, the stationary plume that explains why you would have potentially a high spot on a plate not near a plate boundary. So that brings us up to slide number 51. What I'm going to do is stop the recording now and call this part 1 of the recording, and then pick up again on slide 51 so you can take a break, pick up on slide 51 to finish plate tectonics.